Right, ladies and gentlemen, let's continue with chapter 11 on heat exchangers. This is the chapter that I most enjoy of all the chapters in the textbook. It is a chapter that would synthesize a lot of information and work that you've done previously, specifically already chapters 3, when you did it last year, when you looked at the total resistance term of different resistance elements. Then it would also addresses external convection and internal convection, everything coming together in this chapter on heat exchangers. Heat exchangers, HX, is just being used in the literature a lot to indicate heat exchangers. Okay, so what is a heat exchanger? A heat exchanger is a piece of equipment that would facilitate the exchange of heat transfer between two streams at different temperatures T1 and T2. So there must be a temperature difference. So schematically, if that is our one stream T1 and there's another stream T2, convective streams, then there's a heat transfer rate that occurs between these two streams, and normally, as far as I know, or in most cases, there's actually a wall that separates these two streams from each other. So that would be a heat exchanger. Now, to solve heat exchanger types of problems, there are at least 3 types of methods that you can use. In this textbook, we are going to address the so-called LMTD, log mean temperature difference method, and then after that, we are going to look at the effectiveness NTU method. Those are the 2 most popular ones. And then there's a third method that has been published recently, which is based on the constructual theory. The constructual theory is a very interesting new theory. It has been developed by Adrian Bejan at Duke University. You've all done thermodynamics, the first law and the second law. Well, constructual theory has been developed as a new law in thermodynamics. And if you're interested in knowing more about that, then you have to do the postgraduate course, and specifically the course in advanced thermodynamics. Then you're going to do that. Now, an article that has been published last year is an article of Adrian Bejan, 4 authors, and myself, and that was published in 2017, and that makes use of the constructural theory to optimize and select heat exchangers to ensure optimum heat transfer. The thing with this theory that is very special about it is a theory that can be used in medicine, it can be used in finances, economy, etc. So if we think of our conservation laws and laws in engineering, Einstein's law can, for example, not be used in psychology and the humanities, and Newton's law. However, this theory can be used in all the disciplines of science. And this is what makes this theory unique. So this we are not going to address in this textbook, but if you're interested about it, you can go and look at that article. In terms of types of heat exchangers, we are going to address most of this lecture on this topic, just as an introduction, so that you can know the different types of heat exchangers. The first type of heat exchanger is called the so-called double pipe heat exchanger. A double pipe. And there are 2 different possible configurations, but both of them consist of one tube. There's the first tube into another one. Like that. So 2 sketches that shows the same thing. like that. And what I'm going to do now is use red and blue to indicate the two different streams, which are at different temperatures. So with the first type, we will have a fluid at a temperature TH flowing into this tube, and another fluid at another temperature TC flowing through the annulus. So the result would be that we've got a hot fluid in the inner tube, and in the annulus a colder fluid. Okay. So that is the first type of configuration. And the second type of configuration, if we use the hot fluid again in that direction, then the cold fluid is going to be directed in the opposite direction. So therefore, in this case, we've got the flow in the inner tube in that direction, and the flow in the annulus at that direction, to the opposite direction. So this is called a parallel flow heat exchanger. Why? Because the flow streams are parallel towards each other, and this one is called a counterflow heat exchanger. Counterflow, because the two flow streams are in different directions. Take note, I've indicated this as the hot stream and that the cold stream. It can be the other way around also. This is just an arbitrary selection. The hot fluid does not always have to flow through the inner tube. These two types of configurations has totally different characteristics in terms of the temperature as a function of X. With a counterflow heat exchanger, this hot fluid temperature is going to decrease like that, in that direction, while the cold fluid temperature is going to do that. So in the beginning, there's a huge temperature difference, but the temperature difference becomes smaller and smaller in the flow direction. With a counterflow heat exchanger, we've got something like that. If that is the hot stream like that, so let's call that the hot stream, and that's the cold stream. The hot stream characteristics is going to look like that, while the cold stream characteristics typically do this. We do it in blue, like that. So that would be the temperature of the cold stream. This would of course be the inlet temperature of the cold stream, and that would be the inlet temperature of the hot stream. Outlet temperature and outlet temperature. So you can see that the temperature difference in a counterflow heat exchanger, it looks as if it's constant. It's not the case, but in general we do not have this tendency that the temperature difference becomes smaller and smaller. Later on in the chapter, you will in any case see that this type of heat exchanger is much more effective than that type of heat exchanger. So the parallel flow heat exchanger is not really being used that lot in industry. Right, now something that is important with heat exchangers is to try to make heat exchangers compact. And by compact, we mean a large area for the heat transfer rate divided by the unit volume. That is specifically important in the motor industry. Your car radiator is an example where they try to get lots of heat transfer area into a small volume, and they try to do it to be as light as possible, because weight is of course a very important criteria. Now, a compact heat exchanger, there's sort of a definition for it, which is called the area density. The area density beta. Now, if the area density beta is larger than 700 meters per cubic meters, then it is considered as a compact heat exchanger. So think about this. In 1 cubic meter volume, the heat transfer area is 700 square meters. So you can see it's very compact. Typical examples of compact heat exchangers are a car radiator. They are in the order of approximately 1,000 square meters per cubic meter. Gas radiators, gas radiators, which you typically get in turbines. Again, in the aircraft industry, you want those heat exchangers to be very compact and light. They are running typically about 6,000 square meters per cubic meters. And who of you know which heat exchanger are the most compact of all heat exchangers? The value is 20,000 square meters per cubic meter. The human lung. Yes, the human lung is the most compact heat exchanger that exists. And obviously we try to develop heat exchangers to get towards that area. Now, in terms of these compact heat exchangers, I just want to show you a photograph of it. Typical example. There you can see one. I don't know if you can see it very clearly, but there are some holes in that direction, and then there's holes in that direction through the same material. Can you see that? If you look carefully, you should be able to see that. Those things are typically being manufactured in heat exchangers, which are called printed circuit heat exchangers, PCHE, printed circuit heat exchangers. They make use of a method of etching, and with the etching they can typically make channels of 1 to 3 millimeters, and then they do some diffusion bonding, and together with that they can also generate some different patterns in some of these channels. We will get to the patterns a little bit later. But on this issue, you will immediately see that this is now a different type of configuration that we had previously. That is not a parallel flow heat exchanger. It is also not a counter-flow heat exchanger. It looks as if those two directions are approximately 90 degrees from each other. And you are correct. So that brings us to the next type of heat exchanger, in which we have the following two possibilities. So if that is our volume, then this would be a plate, and there will be another plate like that. Many of them much more closely spaced than I'm trying to draw here. Typically like that, schematically. Okay. And here will be some channels like that. And the flow, we will have one flow stream. Let's say that is equal to TH, the hot stream, and then we will have the cold stream TC flowing between the plates. And these are called cross-flow heat exchangers. Cross-flow, so they're very easy to identify in terms of the flow direction, which is approximately 90 degrees. And this is called an unmixed cross-flow heat exchanger. Why unmixed? Well, if you look at the next type of configuration, then you'll see what I mean. With this one, there are no plates. this is just the channels. Okay. And they are like that, that direction. The sketch is not so good, like that. So we do not have this frame of plates. It is only the tubes, like that, and we've got the one fluid going through the tubes, and then the other fluid going over the tubes in a perpendicular direction. I think the following sketch would show it much more clearly. So the first type is an unmixed type of cross-flow heat exchanger, and this one is called a mixed type of cross-flow heat exchanger. Is that clear to you? Okay. The next type of heat exchanger is called a shell and tube. A shell and tube heat exchanger. That is a very important category. And it consists, firstly, of, as it says, a shell, like this. Okay. And as part of it, there is a so-called front-end header. So that is called the shell, the outside cylindrical configuration, keep everything on the inside. This is called the front end header. And this is called the back end header. So the header is where the flow is being distributed. And let's look at the flow stream coming through there and going out there, and it is done through many tubes like this. I'm just going to put in 4 to make things to look more simple. And again, the hot stream or the cold stream can be opposite to what I am drawing here. But let's suppose this is the hot stream. So the hot stream fluid will come in here. This is why it is called a header. It just distributes the fluid so that it flows through these tubes in that direction. Okay? And then it is flowing out again like that. Okay. This is TH inlet, that is TH outlet. So normally this temperature, if it's a single phase fluid, would be lower than this temperature, except if there's boiling and or evaporation and or condensation. But we will get to that a little bit later. So what we see now is only the one stream. Now we have to put in the other stream, and the other stream we are going to put in there and put in there. It can go out there like that. So this stream, inlet is there, and outlet is there. Okay. Now the first thing that you would think is that this is the flow stream, and now the flow of the colder stream is in this direction. It is, they have found very quickly when they start boiling these, that it is much more effective if they can change the flow path to be in the cross-flow direction, and in that direction there, and then again in that direction there, like that. And they do that by putting in baffle plates. So there's a baffle plate, like there, and then it allows the flow, it forces the flow in this direction, and then there's a buffalo plate again into that direction, forcing it to come down, then to change direction again into that direction like that. Okay? So that is called a shell and tube heat exchanger. Of course, that is the shell, and these are the tubes. Let's just put in the TC and TC outlet and TC inlet. Okay. Now the shell and tube heat exchangers are being used a lot in industry. However, one of the disadvantages is that it has a large size and weight. So normally, if you've maybe done a design project or a research project and your heat transfer rates are in the order of magnitudes of 1 or 10, then this is not a suitable type of heat exchanger. So normally these types of heat exchangers are on the order of magnitude of 100 kilowatts and more. Then they start becoming very economically justified, even although they've got a large size and weight. Now it can be very effective. So let me just show you a better picture than the one that I've tried to draw. So there you can see it, it's in your textbook, schematic of it, and there it is in little colors to make it more clear. There you can see that how the baffle plates are changing the direction. There's typically one that can open there at the front end header. There you can see all the tubes. But there you can see some of the tubes typically, which will be used in one of these shell and tube heat exchangers. So now you can see immediately there's a very interesting change in the sense that if these are the tubes, like that, you can start doing very interesting things by, if that was now the hot fluid going in there, then you can connect those two tubes like that, which then means that that flow direction switches into this direction. And you can do it only with 2 tubes, or you can even do all 4 of them, typically like that. So there are many, many different configurations that can be installed, and in terms of the very specific characteristics, the advantages and the disadvantages, later on into this chapter we will get to graphs and equations that you can use to make these types of decisions in terms of what direction you want to go. So there's another one under construction where you can typically see the tubes also, typically a few hundred of these tubes. What is also important is that these tubes, the nearer you space them, the more compact you make the heat exchanger. However, cleaning is in many cases a problem. So there are industry standards which are typically called the TEMA standard, and the TEMA standard would typically prescribe that these tube distance, the minimum should be 1.5 times the diameter of the tube. That is to ensure that cleaning can be done between the tubes, and in terms of cleaning and or fouling, we're going to get to that a little bit later on in this lecture. Right, the next type of category of heat exchangers are called plate and frame heat exchangers. Plate and frame. Okay. Now these category of heat exchangers, again, what you're going to have is a plate and more plates, quite a lot of them. And what you're going to do now is, between the one plate, you're going to distribute the hot fluid, TH, and between the other one, the cold fluid, maybe in that direction like there. As the name says, it is plates which are normally put into a frame, and there are 2 different types that can be manufactured. There are some of them which are brazed, but then there are some of them that's in a frame with nuts and bolts, and you can open them. Typically in the milk industry, where they have to clean it every day, you can take it apart, you can clean it, and you can put it back together. Of course, the big challenge with this is the sealing, making sure that there cannot be flow from the one type of heat exchanger plate to the other type of heat exchanger, and except for the fact that it has plates, what you can start doing with these plates is, if that is the plate, you can start doing very interesting things in the sense that you can bend the plate so that the flow can be forced in a zigzag direction. Okay. And I'm going to show you some examples in that regard. So there you can see it. We put it together, all the different plates. You cannot see the patterns that clearly on the plates, but in principle, that is what you do. The hot flow, the hot stream and the cold stream, the hot stream and the cold stream, etc. There you can see how some of these plates are being bent and the different types of channels. You can see some more detail on it, and you'll see the seals there, the packaging, which are also quite complicated to ensure that the flow is from one stream so that the streams do not mix. The next type of heat exchanger is called the regenerative type of heat exchanger. Regenerative. And the principle of this heat exchanger is normally you've got a geometry, normally cylindrical disc, and normally it is a porous medium. Porous medium, almost like steel wool, and it has usually quite a large weight. You can use steel, something like steel wool or a ceramic wire, and the result of this is that you can do actually a lot of heat storage. And in principle what you do is you separate the one stream from the other stream like that. This would rotate like that, and then you're going to have the hot stream that would heat this big porous body, and as it then moves around, you will have the cold stream that will be exposed to the hot body, and that is how the heat transfer occurs. An example of that, there's a sketch typically of how it looks like, much more complicated than I've showed there, but there you can see the principle of what really happens. Right, so this is just a very quick overview of the different types of heat exchangers that you're going to be exposed in this module. Now, let's get to the mathematics, or the mathematical description of it. What is important with heat exchangers is the overall heat transfer coefficient. HTC, remember, is the heat transfer coefficient. Now, with all heat exchangers, there's one thing that is common. Firstly, we've got a geometry, which can be a tube wall, a cylindrical tube like this. So this is the wall, or it can be like in a plate, like this. And that would be part of the inner diameter, and that would be the outer diameter. And in this case, it will just be the thickness T of the wall or the plate. Now, with both of them, in general, it is a wall that we have with a certain thickness T, and that we can also express that as the thickness T. we will have a hot fluid on the one side and we will have a cold fluid on the other side. That is the definition of a heat exchanger. And the heat transfer will occur because of convective. This heat transfer to the surface will be because of convective heat transfer. Through the wall, it will be through conduction heat transfer. And then from the wall to this stream again, it would be convective heat transfer. So it's a problem that consists out of a combination of convective heat transfer and conduction heat transfer. Radiation, if there's a radiation, we will normally add to this term. To make things easier, we will add the resistance of the radiation to one of the convective streams. Okay. Now you've already done it in chapter 3 of the textbook of Cengel and Ghajar, where this wall resistance can be written as the ln of the diameter ratio divided by 2 pi KL. Okay? That would now be for a wall, which is part of a cylinder. While if it is a two-dimensional type of wall, more in a 2D direction, then it would just be the thickness divided by K and the surface area. I don't know if you can still remember that. And in general, so that would be the conduction resistance terms, and the other resistance term would of course be that of convection. And the convection heat transfer would always be 1 divided by the heat transfer coefficient multiplied by the area. If you cannot remember that, just go back to chapter 3 in Cengel and Ghajar. So it therefore means that the total resistance consists always out of 3 terms. We will have the resistance on the inside, the resistance of the wall, and the resistance on the outside. Let's suppose you've selected that as the inside and that the outside, or side 1 and side 2, it doesn't matter. In this case, maybe you can call that the inside and that the outside. Here also the inside and the outside, it doesn't matter. Thus, so if we look at a body which has this type of geometry, cylindrical of nature, then the total resistance would be equal to 1 divided by the heat transfer coefficient on the inside multiplied by the surface area on the inside, plus the ln of the diameter on the outside divided by the diameter on the inside, divided by 2 pi KL, plus 1 divided by the heat transfer coefficient on the outside, the area on the outside. Okay, to be clear, area on the inside would be that surface area there, and the area on the outside would be that surface area. You agree? Okay. Now, if it is a 2-dimensional type of geometry, like a wall, then the total resistance would be 1 divided by the heat transfer coefficient on the inside multiplied by the area, and the area is a general area because it's the same for the inside and outside, plus T divided by Ka, plus 1 divided by the heat transfer coefficient on the outside multiplied by the area. And here you can see that in the case of the wall, this area on the inside and the outside are in many cases the same. We will later on see that most probably this is not an effective heat exchanger and what you can do to make it more effective. But in terms of these resistance terms, what is very important is that we can say that the total heat transfer rate is equal to the delta T divided by the total resistance. The delta T would of course be the temperature difference. So we can write this as the temperature on the inside minus the temperature on the outside divided by R total. What we also can do is we can write the total heat transfer rate as equal to U multiplied by the area multiplied by delta T, where U is being called the overall heat transfer coefficient. U is called the overall heat transfer coefficient. And you can also write it as in general like that, or you can write it as the overall heat transfer coefficient on the inside multiplied by the area on the inside multiplied by delta T is equal to the overall heat transfer coefficient on the outside, the area on the outside multiplied by delta T. Thus, in general, we can say 1 divided by the overall heat transfer coefficient multiplied by the surface is equal to 1 divided by the overall heat transfer coefficient on the inside multiplied by the area is 1 divided by the overall heat transfer coefficient area is equal to R, where R is equal to 1 divided by the heat transfer coefficient on the inside, area on the inside, plus the resistance of the wall, plus 1 divided by the heat transfer coefficient on the outside, area on the outside. So take note that this has now been written in terms of a case. I'm going to show it like this, where this is the temperature on the inside and that is the temperature on the outside, and we've looked at the small type of control volume in the Z direction. I hope you will remember that we have found that when you now typically look at this total heat transfer area, that the temperature on the inside stream is going to do that, the temperature on the outside is going to do that. So in practice, the problem was, what delta T do we use? I've already showed to you that using the bulk temperature is not going to work. So what we can actually say already at this stage is that in general, this should be the LMTD. It is coming up in the next section of the textbook, but let's just write it there. Let's just write it like that, so that in general you cannot make this mistake when you start working out problems. Take a look at that, and before we go on, and tell me if you've got any problems with that or any questions. So why do we write it like this? This overall heat transfer coefficient, why is it important? It is important because many people that manufacture heat exchangers here are some more slides in terms of different plates. I've got to show you that. There's a big Shannon tube being constructed. Yeah, what I want to show you is table 11.1. So in table 11.1, different values of U is being given. So when you do the design of the heat exchanger, you can get this from the manufacturer. By giving you this value, you do not have to go and calculate the heat transfer coefficients on the inside and the outside, and the resistance of the wall. So it saves you some time. So normally, you're going to make your selection from there. What is, however, important to note is that this shows you that you have to be careful for the overall heat transfer coefficient. if somebody gives you the overall heat transfer coefficient, then your question should be based on which area. Is it on the inside area or on the outside area? That is not always an important and relevant question, but in some cases it is. In this case, it's not going to matter. Okay. But in many other cases, it is very important. So if you look at this, then all of you should now be able to design a heat exchanger. If I give you a certain geometry, you're going to have the two channels, the inside and the outside, and from either external convection or internal convection, you should be able to get the heat transfer coefficient, you should be able to plug it in there, and you should be able to calculate the total resistance, and from there you can calculate the heat transfer rate for a certain temperature difference that you need. However, what I want to warn you against is not to be like a parrot and just go through the process and do all the calculations. The most important part of designing heat exchangers is to be very critical when you look at all this. And when I say all this, I think it would be things like, is the inside area equal to the outside area? Okay. If the inside area is equal to the outside area, then you'll be able to see that you can take the area out and you can only work with the heat transfer coefficient on the inside and the outside and with that term. So it makes things easier for you. The other thing that you need to check is the ratio of these two diameters. Okay, why? Because we've got a ln term there of the ln of the diameter on the inside divided by the outside. If your heat exchanger wall is very thin and the radius quite large, then this is most probably going to go to 0. Okay. So it means that this term is going to disappear. Okay. The other thing that you need to check is the thermal conductivity K. Because if the wall is thin, then this is going to be already very small. If the K value is large, for example, copper with a value of, I think, 300 watts per meter Kelvin, then again you divide by something that is quite large here, and then that term would also disappear. So you have to be very critical when you look at the contribution of the three terms: the inside convective, the wall resistance, and the outside resistance. You would, for example, if I would say, well, many car radiators are being made from plastic, and that's a good thing. Would you agree with me or disagree with me? So most people would say, no, that doesn't make sense, because when you use plastic, the thermal conductivity is very low. Do you agree? However, with plastic, they can make very thin walls. So this is going to win by far. So plastic heat exchangers with thin walls are being used a lot in industry. They are very effective heat exchangers. Thermal conductivity doesn't play a role. Okay. However, in this critical discussion, it is very important to realize that U, in many cases, is being dominated by one term. And again, I do not want to generalize. It is not always. It's not always the case, but in many cases it is. Let's look, for example, at a case where if the inside area is equal to the outside area, and you start, then you can say 1 divided by U. If you look at this, you can say 1 divided by U is equal to the resistance, is equal to 1 divided by the heat transfer coefficient on the inside, the resistance of the wall, plus 1 divided by the resistance on the outside. Just as an example. Let's suppose the heat transfer coefficient on the inside is 10. The resistance of the wall is 0.401, and the heat transfer coefficient on the outside is about 1,000. Then, if you go and calculate it, then you'll see that is equal to 0.1. That is equal to 0.401, and that would be equal to 201, like that. You see? So what does it really mean? It means that this value, that 10, is your problem case. If you would like to design a more effective heat exchanger, it is not going to help to increase the velocity on the outside by trying to increase the heat transfer coefficient. It's not going to help you to try to change the wall or to change the material from plastic to copper. It's not going to help. This is the one that needs to be addressed. So it means the U is dominated by the one term, and it would be the smallest heat transfer coefficient. Because if you go and calculate it, then that would be 0.1, 2 zeros and a 1, and 0, 1. And there you can see that this 0.1 has the biggest contribution. The other contributions are negligible. Thus, if you've got a problem like this, then you need to see that that heat transfer coefficient is a function of the Nusselt number, HD divided by K, and that can always be written as a constant multiplied by the Reynolds to the M and a Prandtl to the N. Now usually if the two fluids are fixed, then you cannot do anything about the Prandtl number because it's a fluid characteristic. So the only way that you can increase the heat transfer coefficient is the Reynolds number, which is rho Vd divided by the viscosity. Those two are being determined by the fluid. That is a characteristic length. So the only thing that you can do is you have to increase the velocity of the inside to increase the heat transfer coefficient. That is actually one of two things that you can do. It's not the only thing that you can do, but that we will address in the next part of the lecture. Ladies and gentlemen, thank you very much, and then I'll see you again on Thursday.